everyone. Welcome again. Our last speaker of the day is Margaret Regan.
Maggie works.
She's going to talk about exploring the real parameter space.
Yeah, thanks so much. I'm glad to be able to speak at Frank's birthday conference. So to say happy birthday and also wake ourselves up a little bit for the last talk of the day. So in Spain, I promised Frank a sash and tiara, but that didn't actually happen. So instead, I photoshopped one. And so the tiara fit actually really well on top of your hat. So, you know, we'll see what happens in the future with that addition. Maybe it'll become part of your style. No, okay. Well, so now to the math components, right? So what I'll be talking about today is a bunch of different projects that all kind of coincide under this theme of exploring the real parameter space. So I'll describe where these problems come from, and then we mainly use parameter homotopy continuation methods to work through these problems. And then I'll give a little bit of information related to this alternate reality component that Frank mentioned a little bit earlier in the week. I guess it's only Tuesday afternoon. Yeah, we talked about it earlier today a little bit. So let's get started. So what we're working with in all of these problems that we'll talk about today is parameterized polynomial systems. So polynomial systems that you can write down based on some sort of problem in an application. And they depend on a set of parameters. So these two examples here, we have the 5-point problem from computer vision on the left, which has the xi and the yi in the two images are capturing these 3D points in space. And the xi and the yi are these parameters that depend on our data from our specific problem. And our goal, we'll talk about the goal of this problem later and results, etc. And then on the right is a kinematic mechanism where the leg lengths are the parameters for our system. So we have this polynomial system that will answer some question that depends on parameters. So this is that polynomial system for the 5-point problem. And so we have on the left, this is an example, right, of we took some pictures of a 3D object. I like to pretend that you took this 3D object and put like 5 red stickies on it, and then you took pictures and you have that all of those 5 red stickies showed up in the pictures that you took, and then you have those data points to work with. And so this is that 3RPR mechanism where we have this polynomial system. It's a little less nice maybe, but it still fits on a slide, or well, half of a slide, so it's not so bad. And our parameters here are again the square of the leg length, so we don't have to deal with square-rooted values of things. And we'll talk about both of these problems a lot more later. Another one that I'll talk about is the minimally bistable ERK network. So it's a chemical reaction network where the only two-way reaction is this K on, K off here. And we can formulate this polynomial system by setting our variables to be concentrations of certain components of this chemical reaction network. And then it's a set of ODEs where we want to look at the steady states here. And our parameters in this case are the reaction rate values. So there are 12 or 13, I believe, in this example here. And so let's talk about how we actually go through solving these problems. So we have parameterized polynomial systems, but how do we solve them, right? And so let's look at this simple example, right? So we have two polynomials and two parameters, P1, P2, and our two variables, Z1 and Z2. And so we want to find the solutions to that system. And we're going to pretend that we can't just write down the solutions to that system. right? So that's the assumption, right, that you have a polynomial system that you want to find the solutions for, but it's too difficult, or you don't have the ability to write down the solutions as it stands. And so what we do is we set up an initial homotopy where we have this choice of an initial start system, this G of Z. And there's a lot of different ways to choose this start system. This is one of them, which is from a total degree homotopy, where we take the degree of the first polynomial, and we take the first variable to that degree minus 1, and then same with the second variable to the degree of the second polynomial minus 1. And this gives us the total degree start system with the Bézier bound number of solutions. And so if we have this, we then want to take the solutions to this system, which we can write down. And then we want to be able to deform using a homotopy to get to the solutions at our target system, f of z, at some base point parameter. So we have to choose some generic parameter point and say that's where we want to solve our target system. And what we do is we use a linear homotopy with the path variable t to move from g of z to f of z at that generic parameter point to where we can see that at t equals 1, we have the start system and solutions at g of z. And then as t goes from t equals 1 to t equals 0, we arrive at the target solutions to our target system, f of z at p naught. And the convention of going from t equals 1 to t equals 0 is one that we use in the Bertini package and the Bertini software, but there are plenty of, I think Macaulay 2 goes from 0 to 1. So this is semi-arbitrary to go from 1 to 0. But that's what we do here, so that's what I'm presenting on my slide. So what does this look like? So we have the solutions to our g of z that we can write down. We have these 4 solutions. And then we move from t equals 1 to t equals 0. And we are able to arrive at maybe 4 solutions to our f of z at p naught. In this case, it does hit 4. Okay. And so these green paths don't actually intersect, even though it looks like they intersect in this picture, right? But we move along these paths to travel from, say, -1, 1 here, along this green path to hit some solution point of f of z at p0. And now we have the solutions at our target system, which is what we wanted, right? And so how do we move along this path? So we take steps in t to move along this path, and we predict in the direction that we want to go, but then we might not be on the path anymore, and so we have to correct back to stay in some general, like, epsilon ball or epsilon tube around our path. Because as you can see maybe from this previous slide, right, paths can get close to each other, even if they don't. Like, this is a 2D picture, right? So they're crossing here, but they can still get close enough to each other that you want to make sure that as you're tracking along these paths, they don't cross. And so we predict and we correct back to the path to stay on that same path from one solution to then the target solution for the target system. And so generally our software uses classical RK4 to predict, and then some number of Newton steps, maximum 3-ish, but you can change this to correct back. So then what happens if we want to do a different parameter point? And so then we can say, well, we have this other parameter value p at 2, 3, and we no longer have to start all the way from our original start system g, but we can use the non-singular isolated solutions from our original target system, f of z at p naught, to then track those points, those solutions of f of z at p naught, to the ones at f of z at p, our new parameter value. So now instead of having a linear homotopy between g and f, we have a linear homotopy in the parameter values from P naught to P. And so we can see that if we have t equals 1, we're at the start system f of z at P naught. And if t is equal to 0, then we're at this f of z at P. You're like, okay, well, why didn't you just solve this one to begin with, right? Why did you go through the whole first part? And this is where this picture is helpful, right? So what we did, so this is not calibrated the way that I think it is. So we have this g of z, which we had those 4 solutions that we could write down. And then we wanted to solve at this this generic base point parameter value P naught. And what can happen, but didn't happen in the example that I showed you, is that you can, we have this upper bound number of solutions from our g of z, and not all of them are non-singular isolated solutions to f of z at P naught. And so what happens is in this first step on the right here, we get rid of anything that goes off to infinity. That's not a non-singular isolated solution. So then when we want to solve for other instances of the parameters, we can do that in a more efficient way and not have to deal with anything that becomes singular. And so that's shown in the 3 different colors on the left here, where we want to solve for 3 different parameter values and get the solutions to f of z at P for those 3 different parameter values. And this just shows 3. But in many cases, for the applications that we're working with, you want to do hundreds, thousands of instances or more, as Taylor's pointing up, go higher, of these parameter values, right? And so it's important to try and make that as fast as possible. We'll talk about speed things in a second. But so that's why we have this 2-step phase, right? So we want to get rid of anything that's not well behaved in the first step. And then we have this homotopy that's just working over changing the parameter values that works more efficiently. Okay. So now that we have kind of the tools of how we might go about using homotopy continuation to solve, let's go back to some of our applications to really look at how we find these real solutions in some of these problems. And so we're back at this 5-point problem. And so I told you that I would tell you later what the goal of this problem was, and so later is now. So we have these 2 images that have captured those 5 stickies, right, on the 3D object in space. And our xi and our yi are the parameter values, and our goal is to solve this polynomial system to obtain the relationship between the 2 cameras. So the E is an essential matrix that tells you the relationship between the 2 cameras, and there's other very established set of equations that get you from this essential matrix to then reconstruct the 3D object in space. So all we worry about is finding that essential matrix. And so we have this polynomial system, which is what we want. We have the parameters xi and yi. And so how do we solve this? Well, so this problem is kind of special in that it's one of the classical problems in computer vision that has a lot of solvers available. And so there are Grobner basis and resultant-based solvers that Zuzana Kukalova has worked with other people in Prague and other places to have these specialized solvers that work very, very quickly. And they're based on these symbolic methods. We also have numerical methods that work to solve these problems. So John and I wrote a paper, this is my first paper, on randomization techniques, because these are overdetermined systems, to solve the 5-point problem. We did not compare timings. It's just a proof of concept math component there. You can also use homotopy continuation.jl, Bertini, Macaulay 2. All of these work to solve this problem. There's a software that we worked with a large group of people out of the ICERM nonlinear algebra semester. It was called nonlinear algebra, yes. Right? Yeah. And there was a big group of us, computer vision engineers and nonlinear algebraists, if that's a thing. We'll create it now. And we worked together to create a solver called minus. The goal was not to use it for the 5-point problem, so I don't think that's actually implemented anywhere. We'll talk about the problems that it did work on in a moment. But it could be coded into that, and that it could actually be faster.
Do you think it could beat our algorithm?
No, probably not.
Yeah, because that's just amazing.
No. I mean, it's closer.
Yeah, but for other problems.
But for other problems, we'll show the results. But it's, so the computer vision engineers like things to be solved in really microseconds. And homotopy continuation does not work quite that fast. But the minus software gets close, closer than I expected it to get. I don't really remember the exact times, but I think it's like 600 milliseconds or something. So it's closer. Yeah. So the common theme for all of these is we find all the complex solutions, and then we filter out the real ones, and then we compare among all the different parameter values that you run, right? So you run for 500,000 whatever instances, and then you have the solution that matches across all of these. Or there are times where maybe you'll take a 6-point and you'll match what what includes that 6-point as well. So there are options of how to choose that solution, but you're solving over complex things, right? And so we use homotopy continuation in that minus software to be able to solve more complicated problems that don't have the symbolic methods that are able to actually work in all instances of these problems. So here is a 3D reconstruction problem that's with 3 cameras, and the 3 cameras are needed to provide all the necessary information and data to have the right, to create a minimal problem, so to create a finite number of solutions and make it solvable. And so in these cases, a lot of times there's some blurred areas or it's hard to differentiate different textures in the images. And so there are 3 cameras, and we have 3 points and 2 lines. And we called it the Chicago problem. It's called the Chicago problem because there are 312 solutions, and that is the area code to phone number, at least one set of phone numbers in Chicago. I feel like with the addition of cell phones, it's not. That was all of it? Okay, that's the main one. So we also have a Cleveland problem. So if you look up the area code for Cleveland, you'll know how many solutions that one has. And so we have 3 cameras, 3 points, 2 lines. The assumption, all the cameras gather all this information. So we're not working with any partial visibility or anything. Tim Duff has done other work on that. But this is 3 points and 2 lines. And again, we want to reconstruct the 3D image. So similar goal as we had for the 5-point problem. We're just more difficult now, right? And so here's a real set of data that we use to test our minus software on. And so you can see in these pictures, right? So it's a triple of images. So these 3, quote unquote, belong together. And then this is the bottom set, or another triplet. And you can see the difference in the 2 triplets, right? So the first set on the top, it's much lighter. You can see the can a lot better. You can identify differences in the lighting a little bit more, or the objects that you're working with. And the things in the images in the bottom 3 set are a little more obscure. There's more shadowing. You can't see the can in this first picture, or at least most of it. You can maybe see that little bit up there. And so it's harder to identify things. It's not as clear as the 5-point images that we would work with, right, for the 5-point problem. And so this is a more difficult problem. And for the first set of images, this first trio, there is a solver that exists that's not homotopy continuation based that can reconstruct this 3D image, right? So give it the data and it can work. And ours can do the same. So the homotopy continuation solver and the other already established solver can both find the solution for this top instance. And that's shown, so on the right here, well, in both of these cases, the green is the ground truth of the cameras. So we have 3 cameras, and the green part is the ground truth. And then it's a little bit hard to see in this upper one, but blue, the blue outline is for the other solver, the solutions for the other solver, and the red is for ours. And so it's kind of hard to tell the 2 different colors because they match relatively well, and they have similar error with respect to the ground truth. Yes?
Are the pictures normalized so that the leftmost camera is like aligned for all of the solutions?
So I think we set the first camera to be at the origin in all of the cases and then translate and rotate from there. And when this comparison is done, it's all like put on the same affine patch, right? So what I want to show in this second trio of images that I went on about how they're more difficult to see different features, right, is that the solver that already existed before our homotopy continuation solver, that actually fails. It doesn't find a solution, but our homotopy continuation solver does find a solution. So, okay, maybe it's a little slower, but it finds the solution at least, right? So this comes in like you're weighing pros and cons, right? No solution or an order of 10 or 20 slower, right? I don't, depends on who you are with which choice you'd make maybe, right? And so this at least shows the power that homotopy continuation methods have in at least being able to find the solutions in some of these more complicated settings. And there is some work that has been done to create some optimized algorithms to increase the speed. Okay, well, I said the common theme in these other methods was that we solve over the complex numbers and then we filter out real things because these are instances where you want to actually have you have everything in front of you so that we care about the real solutions, right? And so one of the ways that we can maybe make our algorithm more efficient is, well, if we only want the real solutions, oops, too far. If we only want the real solutions, can we get rid of the complex ones, right? And so with the 5-point problem, there was some analysis that we did to try and say, okay, if we look at just the imaginary part of the path, so if we look at the point on the path in the homotopy, so this is not the homotopy path, this black line. This is the size of the imaginary component of the homotopy path. So we're moving along those green lines that I showed you at the very beginning, right? And we're saying, how big is the imaginary part? If it's really big, it's never going to become 0. Never is heuristic, right? But so we did this based on some heuristic angle value that we chose, right? So if this is large enough at some value of t, we're not going to make it back to 0. And so we just stop tracking that one. We say goodbye. We don't do anything else. We stop doing those computations, and we move on to the next one. But if it's small enough, if it's close enough to 0, then we say, okay, we've got to keep going, right? And some of these words up here I didn't talk about, but the key part that I want you to take away from this table is that if we track the average number of steps to get from our start solution to our target solution, in these cases, among all the paths that we have to track. So for the 5-point problem, this is 10 solution paths. Doing all of the paths and adding no truncation, we took about 14 steps along that homotopy continuation path with our predictor-corrector method. And adding in this truncation allowed us to decrease that average number of steps, right? We weren't interested in optimizing this software to compare timings, right? So that didn't seem like a good comparison amongst the different solvers that we have here. I can talk more about those offline if you're interested in hearing the other details of what the SVD, leverage, et cetera means. But the key part here, right, is that we can decrease the number of steps if we truncate, right? So there is a computational benefit to getting rid of things. The question becomes, do you still get all the real solutions that you want, right? And so for the 5-point problem, we knew which ones we wanted, and so we could set the heuristic to be what we needed it to be. But that's the big question, right? Can you do this in a way that allows you over the course of all of your 500,000 whatever amount of parameter runs that you still enough of the time get the solution that you want, right? And that's something that we didn't incorporate into the minus software, for example. So there could be other ways to implement speed ups in that sense, to stick with homotopy continuation and be able to solve the harder problems. Okay. Well, so another piece is that what if we can just track real solutions to real solutions, right? So we said that we only care about the real solutions. So what if we just get rid of, at a certain point along the homotopy path, we just get rid of the complex ones if they're not going to become real? But what if we just track real to real instead? Can we do that? And generally, you can't because you hit the discriminant locus. So if we look at this purple line, so this, nope, that's going next. Okay, here we go. So we have this purple line here, right? And so the purple line is crossing, so the different colors here so the boundaries between the different colors represent where the discriminant locus would be in this case, right? So in the red component, we have 0 real solutions, and then we have 2, 4, 6, and so it's colored based on this number of real solutions. And so if you just took any point in the parameter space and then tracked to another point in the parameter space, so this is like our f of z at p naught and f of z at p, and we want to track between the two. If we just use normal parameter homotopy continuation, like what I talked about before, there's no worries, right? We can get from the first parameter point to our target system. We're working over the complexes. Maybe you add in the gamma trick to make sure you don't hit anything nasty, right? And you're good to go. But that wasn't the point, right? We wanted to just be able to simplify things and only track the real solutions. But that's where the discriminant locus comes in. That's why we don't generally track over the real solutions, right? Because the purple line is a perfect example, right? What if you started here and you wanted to track over here? Well, if you tracked over the reals, then you're going to run into the discriminant locus, and you can't necessarily say that the solution you had at the beginning corresponds to the solution that you arrive at the end. But if we have this picture of the discriminant locus, if we're able to understand the location of the complement of the discriminant, of the connected components of the complement of the discriminant locus, then we have the ability to take a point that we say we want to find the solutions at the bottom of the black line. So corresponding to the parameter point at the bottom of that black line to the right. And we say, okay, well, we have the solutions here. And so we're going to take just a real parameter homotopy from that start parameter point value at the top to the bottom. And if you have, so this becomes a sampling kind of problem in the sense of Well, if you have points that are really far, like these are kind of far away from each other, so in general you would think, well, maybe if you had a point that was that far away, wouldn't it have a higher risk of running into the discriminant locus? But if you have points that are a sample set that is close enough to each other, then you should be able to have the data from a parameter point that's in the same connected component where you wouldn't run into this issue. You would be able to do a real parameter homotopy from one point to the other, just track real solutions to real solutions. And we did this so the picture on the previous slide was for the Kuramoto n=3 case, so this is an oscillation problem. And the key part is not really what the problem is, but instead, when we did this classical homotopy that tracks all the complex solutions, it took about 1.33 seconds. So this is tracking, it's a total number of 6 possible solutions. And so we have 2, 4, and 6 possible real solutions in these connected components that were shown on this previous slide, right? So we have orange is 2, yellow is 4, blue is 6. And so we tested it on data points that show up in each of these cases, and the time took less than 0.1 seconds in each of these cases. And the success rate was 100%. So what that means is that we never ran into this purple line situation. And so we did see a speed up, and we saw a similar speed up right in the next case where we have 3 parameter values for the n=4 Kuramoto case. We had general usual homotopy, classical homotopy, 3.4 seconds. And then we went down to 0.15 seconds about. So we saw this speed up. And that's when there's only, so the n=3 case for the Kuramoto model has 6 maximum complex solutions. So if you're comparing tracking 2 solution paths versus 6, like, okay, cool, I guess. And Kuramoto model n=4, you have 14 possible complex solutions, and the maximal number of real solutions is 10. But even the difference between tracking 2 real paths and 14 complex paths, it's like, okay, you know. But for the Chicago problem, for example, there are 312 complex solutions. And so maybe this could be impactful in that case if we had an understanding of these connected components of the complement of the discriminant locus, because there are on average only 40 real solutions out of those 312. And so when you're tracking a subset of 40 real solutions versus 312 solutions, and the polynomial system is much more complicated, of higher degree, et cetera, could this benefit be much larger? Especially in an instance where speed is cared about, right? So that's another option, okay? And then we can go even further and say, what if we want real positive solutions? So now we care about whether things are positive as well. And so what can we do to use numerical algebraic geometry to look at the real positive solutions? And so we're back to our chemical reaction network system that I showed you at the beginning, where we have this set of ODEs. We want to find the steady states to these. So we want real positive steady states to this system. We care about what does it mean to have a negative chemical concentration of something, right? So positive makes sense in this scenario. And so what we did was we did a similar sampling of our discriminant locus, right? So what we did was we took linear slices of our parameter space. So we said, so these are our 2 parameters. I think this axis is k on, and this axis is k cat, which are 2 of the parameters that show up in this. So here's k cat, for example, and then k on somewhere else. It's small. But these are 2 parameters that are reaction rate constants for our polynomial system. And we took linear slices to find points on our discriminant locus. So these are witness set points. And so what we have is, if we take our polynomial system and the determinant of the Jacobian and this linear slice, then we're able to get witness set or pseudo-witness set points that lie on the discriminant locus curve. So when we don't actually have the polynomial for the discriminant, we're still able to sample on the discriminant and get some general picture of what the connected components of the complement of it look like. And what this does is it allows us to separate the parameter space into regions where we can label. So the blue part is 3 real solutions, and the yellow part is 5 real solutions in this case. And it actually turns out when you look at how many are positive, it's just 1 everywhere. So it's 1 positive real solution across the entire parameter space. This is everything above, like greater than 0, right? And so 1 positive real solution, even though there's this separation between 3 real and 5 real, there's only 1 positive across the whole space. And so the reason we are studying this specific network is because there's a conjecture on the maximum number of positive real solutions. And so could we find that? Could we show that that is true or not true, right? And so the upper bound based on a mixed volume computation is 5, and I think Elise Walker and Nita also showed it for Khovansky bases, right? Showed that the maximum number is, the upper bound is 5, but the conjecture is that there's really only 3. So there's really only 3 positive real steady states. And so could we find 5, or could we prove that there are only this maximum of 3? And so I apologize, the colors are not done. Anyways, these colors are flipped across the 2 pictures because I really wanted to challenge your brain at 4:39 on a Tuesday. So what the blue on the left and the red on the right show are the discriminant these sample points on the discriminant locus, right? And then the red over here and blue over here show the how the positivity of the variables changes. And so we created this breakdown of the parameter space. I did this with my undergraduate student at Duke. And we were able to show that these regions labeled 1, 4, and 7, so we can kind of ignore the blue curve here and the red curve here. And this region obtains 3 positive real solutions. And so, okay, we showed that we can achieve this 3, which was the conjecture of the upper bound. That doesn't mean you can't achieve 5, right? And so there are a couple of questions that go along with this, right? Of, can you certify your sampling of the discriminant locus in some way when you don't have the polynomial to say that at least in this snapshot of the parameter space, you've gotten everything. You have all of the connected components that are in the complement of the discriminant locus, so you can at least say in this snapshot of the parameter space that there aren't 5 solutions. Well, there's an added complication to that, right? Because this parameter space, while it goes over values of k-on and k-cat, I don't know if you remember from like 35 minutes ago maybe when I told you that there were 12 parameters. And so this is just looking at 2 of those 12 where we set a parameterization of the based on like of a relationship base related to all of the other 10. And that was developed with a Newton polytope computation that Nita Obataki did to show that this was the parameterization of the parameters that yielded that maximal number of 3 positive real steady states. But is that the parameterization that would yield the upper bound, right? I don't know that we know that. And so that makes it a little bit more complicated, right? Okay, I think I have time to get through all the rest of it, so we're gonna keep going. So one of the other things, the focus so far has been finding real solutions, or maybe positive real solutions, depending on what problem you're looking at. But can you analyze the behavior of the real solutions and understand the structure of how they behave? And this connects to some of the concepts that Thomas was talking about last talk. And so can we see how real solutions interact with each other? And so we're back to our kinematic mechanism here, where, like I said, the parameters are the leg lengths. So our legs can grow and shrink, and we want to see how the orientation of this mechanism changes as those leg lengths grow and shrink. And so can we set the leg lengths and then move along a path in the parameter space, so grow and shrink the legs, have the orientation then come back to a different orientation of this triangle when we land back at the same value of the leg lengths, okay? So what we did was we used the discriminant locus again, or a sampling of the discriminant locus, because we don't have the polynomial, to be able to try and answer this question of how do real solutions interchange with real solutions. So again, we have this parameterized polynomial system. Our parameters are squares of the leg lengths, and we have 6 non-singular real solutions. So 6 is the maximal number of solutions for this system, and there is a point where we can achieve 6 real ones out of the total. And so we're able to find these 6 real solutions. So as I described before, right, all of these leg lengths are the same in all 6 of these images, but the orientation of that platform, the triangle, is different. So we can visually see how different they are with having the same leg length values. And so how do we know whether, how can we determine whether or not we can take the leg length values, travel in a loop in the parameter space, end up at the same leg length values, but maybe go from 1 to 5? Can we interchange that orientation? And so here's a picture of the discriminant locus. And so the white portion here has 0 solutions. Then we get 2 in like the cyan. And then as the color gets darker, we keep adding 2. And so in the dark blue region, we have that maximal 6 real solutions. That's where we consider it our home base. We said if we start at that home base parameter point, can we take loops and switch our orientation, end up at a different solution at that same point? And so the answer is yes, we could. We did have an interchanging of solutions in this case. And so we have this base point, right, that I said was our home base, this point A. And then we moved along this path. We went from A to B, B to C, C to D, etc. And we ended up back at our original point. So this bottom part is like moving in a path in our parameter space. And then we tracked what happened to our mechanism as we moved along that path. So our legs are growing and shrinking. And then what happened is we ended up with the mechanism at the top. Sorry, we started with the mechanism at the top, and we ended up with the mechanism at the bottom, where we can very visually see, right? So these live over the same parameter point, so our leg lengths are the same, but the orientation of our platform is different. And so we do have an interchanging of these 2 solutions here. And what it turned out to, what ended up happening was that, so if we go back to these 6, they're labeled in this way for a reason. What we ended up seeing was that these three could interchange with each other, and these three could interchange with each other, but they couldn't interchange across those trios. And this was structure that was missed with the complex, like looking at the interchange of the complex solutions, which just showed that it was a full symmetric group. And so being able to look at the real solution interchange allowed us to see this underlying structure in these two groups of three that didn't show up if we looked over things of the complex. And we knew a priori that this structure existed by work by Manfred Husti. And so we were trying to say, okay, can we give a description of this real monodromy action based on just the real solutions to capture this behavior that wasn't shown by looking at the complex solution set?
You're saying that Manfred realized there's something special about these two sets.
Yes.
I wanted to see if you're monitoring.
Right. So he saw this structure of these two components, where there were three solutions that could interchange, that existed on one, and three that existed on the other.
So this is a purely real phenomenon.
Correct. Yes. This one. So we're doing complex homotopy continuation, but I was no. So we were using complex homotopy continuation to see, and so the reason for all the points was to say, okay, if we went from here and essentially crossed through, but in complex space, right? We would, which path stayed real the whole time? So which solution stayed real along that whole path? So we are still taking complex paths, but we are making sure that the solution stayed real across the path the whole time. So if the solution disappeared, so we had an ordering of the solutions over here and an ordering over there, and so we knew which ones disappeared and so they went complex and which ones were real. And so the computations were still done over the complex numbers. Okay, so in the last few minutes, I'm going to discuss some questions that I've been exploring with Frank and Simone Tellen about something that Frank's mentioned and was brought up earlier with the isotropic coordinates that Charles mentioned of alternate reality. So it makes me kind of think of the X-Files, but I was told that maybe that wasn't the right comparison to make last night. But all of the work that I've been discussing so far is with the standard real structure, right? Which we know how to visualize, we know how to work with. We have all of these softwares and symbolic methods, numerical methods that allow us to analyze what happens to our number of solutions, or what is the singularity structure in the cases of these parameter values, which we don't even have all of that information, but we have a lot of information that allows us to solve problems in this way. But what happens if we don't have that standard real structure? And so one of the cases that will show up, this example will show up some in Matthew's talk later in the week in some form. This example might show up. But so if we look at what happens with the Schrodinger operator on the hexagonal lattice that underlines graphene, we have real parameters A, B, and C, and we have real potentials U and V that define this structure. But we have an alternate real structure based on the torus, right? And so how do we work with being able to describe the critical points of this variety? And so what we do is we look at the Fourier transform applied to this hexagonal lattice, or the matrix that describes the hexagonal lattice, where we are able to look at the spectrum, and we have that this spectrum becomes the block variety. And we want to look at the critical points associated with this block variety. But how do we do that with this alternate real structure? And so we've made some progress in being able to characterize the critical points based on whether or not the potentials are equal to each other. And so in this case on the left, the potentials are not equal, and so we have a spectral gap here. But when the potentials are equal to each other, there is no spectral gap, so you can see these 2 points where it closes. And so there's a special structure that happens there. But we run into some blocks when we go into cases with more edges and more parameters that make it hard to compute or visualize, because the degree and the dimension of this problem, when we move from the non-standard reality to analyzing it in the standard case, it just becomes that much more complicated. So how can we even begin to start answering these problems of analyzing the effect of these real parameters and how that changes the critical point structure when we're working with this non-standard reality? And so the answer isn't quite clear, but this is a new avenue to maybe start exploring, because it does show up, and so these are related to problems in physics. Okay. And so, okay, well, I may be 2 minutes over, and I've said most of these things already, but can we use the real parameter space to say this is the maximum number of solutions? Maybe can we always guarantee that there's one real solution? Can we certify what we've found with sampling to show that, at least in the snapshot that we have, that it's captured everything when we don't have the ability to solve for the discriminant locus polynomial? And then can we do all of this if we're in non-standard reality, right? So thanks for listening. This is work with a lot of different people, so it's not just me. And thanks so much.